Oh, he wants to start like a history reading.
Okay.
Oh,
It's
him,
on.
not me.
Okay, it actually doesn't.
I'll do it if
This is
we
just
I'll do it if we throw in at least one
As
philosophy.
long as that's pictures.
All right.
Yeah.
I'll just hand
Let's do it.
about.
Cool.
the-
I want to read Durkheim.
They have to have artist depictions, okay? Or I'm out.
It was the suggestion of the thing to read next from.
All the started between 4 and 60 pages.
Do you want to get started?
I can get started.
It's a question best interesting you. The one announcement I have is that I got an email about this SANS. It looks like a hacking as in black hat competition. And there is I guess a sort of online seminar / an online lecture about it, and its format on the 27th, which is a Tuesday, and it looked really interesting. And I will definitely be going to watch the online lecture. And apparently they are screening it, second floor of Sears. It all got sent out to the Hackers Discuss list, which is why I didn't bother to really memorize it. Okay.
So, hi guys. I'm giving a talk on Tempest. And to start with, I would have a little disclaimer, and that is, if you've read about all of the amazing things you can do with Tempest, I'm not going to show you anything that's completely mind-blowing today. Although I do have a bunch of different demos. And part of that is because it's really the realm of the military, by and large. A lot of the information about Tempest is highly classified. People send in FOIA requests all the time, and all they get back is wasted toner. And so the other thing about it, though, is that it's simple enough of a concept that you don't really have to ask them how they do it because you can figure it out. Tempest falls into the realm of both signals intelligence, which they call SIGINT. And so Tempest itself isn't actually about looking for things. Tempest is about protecting yourself from attacks that would use signals intelligence techniques. And the majority of these signals would be electromagnetic waves. Yeah, that's a really good idea.
Then you can do it so you turn off the purple.
So,
The other one.
hmm?
There's 2 buttons.
Yeah. Oh, it works. So then these are actually something that, for that, but they are called B-field probes, and they're for looking at magnetic fields. I haven't actually tried them yet because Ed was like, hey, I've got these things. Do you want me to give them to you tomorrow? And I was like, okay. So it works. Anyway, the other thing that really comprises the majority of Tempest is electromagnetic or electric fields in the form of radio waves. And that's why today, part of what I'm going to discuss is just general RF knowledge, because it's not something that is really gone over in any case classes, even in double E. I know this, I'm a little bit out of place here, but I'll try and keep it simple with a lot of the demos, and I'll be happy to answer any questions as we go along. So that is a picture of a 900 megahertz RFID tag. There's one of those in every single train car in America. They track the movements of freight at different points around the country, and it just so happens that they're fairly easy to read, although I won't be demonstrating that. What I mean by that is we forget how many things there are in the world around us floating around, beaconing off information. Sometimes that information is obscured from us, but often it's not all that hidden. So first we could go over, say for example in the case area, what signals, if you were curious, could you listen to? And I'll show you something called the Universal Licensing System from the FCC in a second. But there's something funny about this clock. Does anyone know anything about these clocks?
Yeah, radio. Yeah.
They're really cool. Also, I pulled it off the wall earlier because that's really weird. Not that magic, but got an antenna in the back. Now, that's because these clocks are synchronized to GPS time when you're inside a building, GPS is really weak, and even still kind of expensive to put in every single clock. So they actually have a 72 megahertz, that's case, a 72 megahertz transmitter for the GPS receiver. Ours is in the law school. CIM also has one for some reason, even though they could just sponge off of ours. And it's funny because there's all this stuff floating around. How would you do this there? I can't actually pick it up down here because I don't have a good antenna for it, but something makes me think that I might be able to pick it up with theirs. Can't really tear it. Pick it up much easier on the north side, but I didn't try it. But anyway, silly little things. And we'll find that frequency here on ULS in a second, and that's how I figured out how exactly cases using this clock system. So before anyone goes up in arms about me opening an Internet Explorer, it doesn't work in Firefox. Although I think it would probably tell me that, oh, I'm Internet Explorer. What do you want to configure me as? Please don't do that. Oh, right. Now this new spiffy FCC. It doesn't look like 1996. This is embarrassing. Okay, they don't know what their own stuff is. So, as all of you may know, the FCC likes to get their hands on everything, but you probably only hear about them in the realm of censoring and maybe some spectrum options. But they coordinate absolutely everything in the country, and almost everything, including a lot of military stuff, is actually on here. Because people need to know where to be and where not to be so that everything works out right. So, if you're curious in your area and say, well, what can I listen to? We could just enter our zip code. And we look at active licenses. Show everything. And hope that it works. So I'll keep talking because it's really slow. Oh, what's that? So all of these people on the left are actually ham radio operators in this. There's case right there. But here you can see a whole bunch of different licenses for walkie-talkies that are unencrypted and you can scan easily. And this one right here is 72.180, that clock synchronization frequency. So, quick little demo. That's a pager. Come on, FCC.
So by the way, how do you know that it's the clock synchronization frequencies? Did you experiment with that and you just know it offhand? Or?
I know it offhand because I have previous experience with the Primex clocks.
Okay.
But if you actually poke around and look at some other information about it, here, I can't remember, oh yeah. They actually have the contact information as Primex because they got the license through them. And so if this equipment is failing, Case doesn't want to know about it, Primex needs to know about it to come fix their clocks.
Gotcha.
So that's actually how I figured it out. So back to this. Yes?
So going back to something you said earlier,
Uh-huh.
does Primex own that frequency throughout the U.S., or did Case apply for it specifically?
Case had to apply for a license.
I'm talking about like the 72.106 megahertz. Does Primex own that 72
No.
megahertz block?
Although it's an area where there isn't that much anymore. And so they built their equipment to handle a variety of frequencies, but Case is required to purchase the license to use it. Yes?
When they bought all the clocks, did they have to individually configure each one?
When they come from the factory, if you buy a bunch of them, they can be set to the same frequency. They have some proprietary programming system. You can actually reprogram them with a button on the back, or do different things that make the second hand do really bizarre things. It's kind of fun, but that's outside the scope of the current discussion. So, other things are all over the place. You may have seen one of these on a water meter cover. This is an automated meter reading antenna, around 900 megahertz, beaconing your water usage. Smart meters are starting to do that, and we'll talk about that a little bit later. But what's interesting is that that presents an interesting tempest risk. We're using interesting twice in a sentence. A lot of the things that you'll be using for these attacks are directional antennas rather than omnidirectional antennas. Because if you know where something is, then if you look at it under a magnifying glass or through a telescope, you'll be able to see it a lot better than if you were to just look at it with your plain eye. And antennas do what they do out of their geometric properties. This is for a much higher frequency than this antenna, but this is an omnidirectional antenna of the type that was invented by the Germans during World War II for Zeppelins, but that's also kind of irrelevant. But all electronic devices are vulnerable to tempest because of their construction. And whether it's from electric fields, magnetic fields, or from radio receivers and transmitters that are inside of them, nothing is safe, to put it lightly. And the reason why the FAA really cares about electronic devices on planes isn't to annoy you as much as it is to get blogs like Gizmo to write about things that they have no idea what they're talking about. That's actually not why. The reason why is that every radio receiver is also a transmitter. And that's because of how they're constructed. Well, I'll say every, not really every, but generally most. So inside a radio, you have a block diagram of something that looks roughly like this. And you have your antenna on this end and your audio on the other side. But in between, in order to process the radio information more easily across a wider range, the radio will down convert or up convert that specific frequency slot, usually down. So say, for example, in an FM radio, if you're looking at 90 megahertz, it'll bring it down to 11.5 to allow for the circuitry inside to only have to look at a smaller portion of the radio spectrum, which simplifies things significantly. Now, the way it does this is by mixing an oscillator signal within the mixer in with the original signal. That's an amplifier, that's an amplifier, that's an amplifier. It then filters it with a bandpass filter. So it says, I don't care about anything outside the range in my IF, they're called, intermediate frequency. And it then is demodulated into the signal that you want. Now, I looked at a couple different radios, and the one on the table is, I was actually kind of surprised I wasn't able to pick anything up out of it. But this radio shows you exactly where it's being tuned to. And the demonstration for that will bridge us into the next quick little topic on some test equipment that some of you are familiar with a portion of it, and some of you are probably not familiar with the other portion. So, say if we were looking for compromising emissions for a device. This is a device called the spectrum analyzer. And instead of plotting voltage over time, like an oscilloscope, it plots signal strength, which is logarithmic and relative, over the frequency axis. And I'll get into how it does that later. But they are much more useful than an oscilloscope for looking at signals because, we'll see why in a second. So I'm going to connect this radio transceiver straight into it. When I turn it on, you see something around the middle. So we see there's a spike coming out of the radio at some frequency near the center. You'll see that the center frequency is up there. I guess for reference, that's the level that the bottom line is. That's the frequency that the center is. And the number on the far right is the width of the entire window. Everything else is complicated. So we'll zoom in on this by sort of expanding the width. And you'll see we've got a nice little spike. It's pretty weak. But this radio currently is tuned to a frequency. And you'll see as I change the frequency on the radio, you can see the local oscillator tuning around to adjust. And what this means is that if you're trying to spy on someone, someone else can spy on you to figure out where you're spying, which is a fairly common theme in a lot of signals intelligence, because not only do you want to have countermeasures of your own, but you want to be finding out what other people's countermeasures are and see what they're doing. Whatever will reap you a tactical advantage.
So wait, so why don't we get to use our cell phones on the airplanes again?
Okay, so the primary concern is that a lot of the equipment, even though it's heavily redundant, works with fairly weak signals, particularly because most aircraft still use a direction finding system that was invented in the 40s that works really well, except is a bit finicky. It works with some interesting mathematical principles
What's it
and
called
different
again?
frequencies. It's called VORs.
Yeah.
Um,
Okay. I've used that. It's a really good system,
It
actually.
is a really good system, and it works really well. However, it is fairly easily interfered with compared to GPS. And they're just spooked that something's going to interrupt them, particularly because in all inclement weather and at night, it's all you really have to go on.
So if I just pull out my GPS, complete receiver, the same issue applies.
Yes, although I've actually had some funny experiences with that. Airlines sort of waffle back and forth on it. I enjoy using a GPS on an airplane because I know how fast I'm going and where I am. And some airlines, like Delta, explicitly allow GPS use in flight, whereas other airlines, like AirTran, specifically disallow it.
So the new wireless that they now provide in airplanes,
Yes.
From what I understand, it's actually provided by ground stations that are operating on a cellular frequency.
Yes.
How is that not creating any more interference than your cell phone is?
Well, that's a good question. And the answer is it's producing more interference than your cell phone ever could. However, the antenna for that is on the outside of the plane. And they know exactly what it's doing, so they feel like they can compensate for it. In reality, I would say that by and large, the spook with the airline stuff that I mentioned as an aside is relatively unwarranted. However, if I were to use something like this and transmit, say, 5 watts of RF, or in the sky, which is 100, I could easily completely mess up anything. I mean, of course, the funny thing is, you can actually buy air communication frequency handheld radios without a license, without any permission. Tune to a frequency, key up, and you're talking to airliners. Someone might be at your door pretty soon, but
You technically need a private pilot's license to talk on that frequency.
you do, indeed. But nothing keeps anyone from purchasing it. Same with all the amateur equipment, actually.
Do you have another question?
Sure.
Oh, sorry, yeah. Just an extension of the whole cell phone on planes thing. Is that related to why they have you shut off all electronic devices?
Yes.
Okay. Because that seems so strange that like you'd have to turn off, for example, your Kindle, even if you don't have one that has.
Well, your Kindle's transmitting, and I'll get to that in a second.
If you, okay. Some people have it on.
Even when the radios are off,
What?
all digital logic is also transmitted. But we'll get to that in a second. Oops, text got cut off. So, back to SIGINT. So as I said, most of it's outside our experience or budget. This is a console in a signals intelligence aircraft with a variety of equipment for interpreting things. You're probably looking at about $500,000 worth of stuff right there. Although that's the military. But a lot of the monitoring that they do is actually on themselves. And so if you have military units who are communicating with each other, you'll also have a division that's listening to the communications to make sure that they're not saying anything where they shouldn't, or saying things that they just plain shouldn't. They call that feed window. And so they have different codes in NATO for disclosing one's position, capabilities, operations, electronic warfare, friendly or enemy key personnel, communication security, or wrong circuit for communications. But there's all sorts of things that you can look at. This aircraft actually specifically operates using something called sonobuoys. They are tubes dropped out of the bottom of the plane. Sonobuoy tubes were what the tidal slide were, actually on the belly of that aircraft. And they use them to listen for submarines using a variety of different methods, either with sound underwater, or for magnetic or electric fields, or alternatively using something called high frequency direction finding that was pioneered during World War II. Because if, say for example, you have submarines that are using encrypted communications, they're still communicating. And so if you can figure out some clever circuit and arrangement of antennas to figure out where that transmission is coming from, you almost have more valuable information than you would just trying to figure out what their encrypted language was. And so that was used to great success to try and locate U-boats. And there was a whole battle between the British and the Germans on the electronic side throughout the war on aircraft direction finding, because the Germans were using it for night bombings over Europe. But interestingly enough, if you were to look at a water meter with one of those magnetic field probes, you'd be able to tell how much water that person's using. And that's because inside a water meter, there's actually a magnetic spindle that couples the information between this special kind of epicyclic disk system used for measuring the volume of water and the recording instrument on top. And so the funny thing is, we, as sort of the whole theme of it, we interact with so many things daily that we don't really even think about could have these bizarre vulnerabilities that could be observed from a distance. But in fact, if you're a military, and if you care, and if you can spend a lot of money on it, you're toast. But let's see. So TEMPEST is illegal. In 1968, what was called trespassatory ELINT, for electronics intelligence, was first made illegal, and that is the concept of sort of climbing around in a telephone closet and trying to wiretap someone, which is fairly obviously not really that okay. But in 1986, the Electronics Communications Privacy Act made all interceptions of non-wire communications not intended for the receiver to come under question. Now, we're not as bad about it here as in Britain, where you can actually get arrested for listening to things that you shouldn't. But for example, in the US, it is illegal, and actually fairly illegal, it's a fairly serious federal crime, to attempt to de-encrypt encrypted signals. And actually a lot of radio devices, you were mentioning this earlier, say on them that, let's see, what will this work on? There we go. Okay, so it's kind of hard to see. Maybe
Hold still.
So now it's just too dim, so I'm going to read it to you. It says, warning, modification of this device to receive cellular radio telephone service signals is prohibited under FCC rules and federal law. Now, it's kind of redundant now because analog cell phones don't exist anymore. AMPS was shut down about 3 years ago. And so with something like this, you'd be picking up encrypted junk and you'd have no idea what to do with it. But they're still fairly serious about it. Laboratory equipment and radios purchased as a government entity are still perfectly capable of dealing with all of this stuff. And GSM still has a funky little vulnerability that they discovered at DEF CON a couple of years ago that I'll talk about in a minute. But TEMPEST is also somewhat irrelevant now. We got into it because the Russians got into it. And we wanted to know exactly what they were doing all the time, and they wanted to know exactly what we were doing all the time. And now we don't really have any enemies where we're participating in significant signals intelligence work with anymore. We have allies that we're snooping. But it is certainly a very Cold War concept, and that really plays into a lot of the mentality of how it works. I actually worked on a project for the Norwegian military a couple of summers ago, where we created a field telephone system that was not susceptible to TEMPEST attacks, because the Norwegians were worried about the Russians. And essentially what we had to do is we had to get rid of any emanations. I'll get to that in a second. But if we were using regular wires, you could construct a sensor that could pick up the signal going through that wire at a distance. Really, no matter how shielded you make that wire, although technically you will get to a point where they couldn't pick up anything. And that's completely how TEMPEST works. But more on that in a second. So what we did was we used, who here is familiar with Asterisk? Okay. Asterisk is an open source PBX software. It stands for Public Branch Exchange. It's a telephone system that runs under its own, is for Linux and also has its own distribution called Trixbox. And what we actually did was all of the terminals on the field telephone are connected to each other with fiber optic cables and run over an IP network, so that no matter how long your cable runs are, no one could snoop on it. And fiber optics are interesting, of course, because it's very easy to detect if anyone's tapping into your line. And the concepts of quantum cryptography play into that, but that's not really what I'm talking about. But for those of you familiar with it, basically, if you're shooting single photons down a line, it's impossible to interrupt that line or measure them without measuring a disturbance at the other end. So we have a couple of pieces of test equipment up here. As I mentioned, oscilloscopes are time domain instruments. They look at distribution of signals over over time, and plot voltage over time specifically. And they're very useful for a lot of different electronics diagnostics tasks, because many signals that we're looking for, are you upside down? You're upside down. A lot of electronic signals that we're looking for are indeed time domain. However, for radio equipment, it's not that useful, and you'll see why in a second. Well, that's really silly.
Looks like it's focusing on those bottom right dots. So maybe if you let's do
Yeah,
that.
I'm doing manual right now.
Oh, okay.
They probably just do it for.
Yeah. There we go.
There you go.
Okay. So we're already picking things up. This is just a wire loop floating around in the air. But let's look at the key fob for my car. Operates around 300 megahertz. Whoa, why is the screen wobbling? That's very interesting. Anyway, never seen that before. So we can crank up the time divisions on the scope way down to the nanoseconds to try and see some sort of disturbance. But because the scope is just looking at voltage and all I have connected to it is an antenna, it has no sort of radio receiver in it to determine what's going on. And even if I pick up some sort of voltage, the likelihood that I'm going to be able to hit or figure out what's going on is slim, because all you've got are these wobbly lines. And if you use your fancy cursors on the scope in the lab, maybe you'll figure out what frequency it is. But there's so many things bouncing around, who knows what's going on? So enter Mr. Spectrum Analyzer again. And this is a spectrum analyzer that operates on fairly analog radio principles. There's really three kinds. And some of you may be familiar with the scopes in the lab. They have what I would call a pretend spectrum analyzer in them. One of the techniques for spectrum analysis is to simply perform an FFT on your waveform to figure out the frequency components of it. However, the issue with that is the window of your FFT will determine your sweep time. And if you want to look at anything that's fairly wide, your sweep time is going to be so long that it's virtually useless. So typically, they are confined to looking at small portions of spectrum. This spectrum analyzer uses a radio and a filter, and actually takes the filter and sweeps the entire bandwidth that it's looking at, and then plots the signal intensity at that specific sweep point. Now, there are some hybrid spectrum analyzers coming out that actually FFT that's turning out to work really well. If you want to get me one, that'd be really great. They're about $50,000. But instead, so we plug in the spectrum analyzer, little antenna. Let me zoom out again. Picking up all sorts of stuff. That big line on the left side, by the way, is DC. Oh, look, maybe that's the signal. So we can dial that in. And there's a lot of different protocols in use. And one of the advantages of a spectrum analyzer is that it can show you what's happening across the frequencies that you're looking at with the signal under examination. And that way, you can figure out how you might be able to decode it. Let's see if this one looks as good as it did yesterday, because yesterday it looked really good. Okay. So do you see how it looks like there's almost a square wave stacked on top of the signal?
Mhm.
That's because this is using something called frequency shift keying, where it literally is putting binary data on top of itself. I really won't go too in-depth on these different things, but I just sort of want to show you, in case you're curious, what all this different stuff looks like. In fact, the cool thing about the spectrum analyzer is that it lets you have some degree of insight about what different things look like, without even having to think too hard. I mean, it's you're like, oh, well, look, that does that, and that's what we're working with. So under here is one of the frequency generators from the lab, and they have some convenient features that allow for you to actually make AM and FM signals. So, any questions on this?
How extensive is the frequency analyzer?
The spectrum analyzer?
Yeah.
So used nice ones go, or medium ones go for about $1,500 to $2,000. This one is actually really cheap and kind of cheesy, and I wish the lab had a nice one, but they don't. But spectrum analyzers are typically some of the most expensive test equipment because they're fairly complicated and not really very commonly used by the majority of sort of the EE population. And so typically they start around $10,000 and will go up to about $250,000, depending on frequency and resolution. I mentioned the filter, and some of these actually will use a crystal made of yttrium iron garnet, which has the interesting property of, if you put it in a magnetic field, it will actually turn into an electric filter that you can tune with the magnetic field. You can also use them as oscillators. It's really bizarre and uses fancy physics stuff, but they're pretty cool. So there's DC again. There's the signal that we're looking at. This guy is actually fairly out of calibration when it comes to the frequency ranges, and that's part of the reason why. It's really good for demos, because you're not going to look into anything I'm doing. So that's your standard sine wave. Looks pretty nice. We turn on AM. You can see that there's actually a sine wave getting stacked on top of the sine wave, going left to right across it. It's a really low frequency AM. It's actually like 100 hertz. If you were to crank it up more reasonably into something that voice would look like, it starts to kind of look like that.
Are Are these connected?
Yes.
Okay.
No, they're actually directly connected.
So if you tune this to an AM radio station, this is what it will look like?
Yes, and actually, um, so you can hear it. I'm tuned to it on my radio. If I change the modulation, my radio can figure out what's going on. But FM is a little different looking and a little harder to figure out. In FM, instead of working on modulating a signal with amplitude to a certain depth, of course, is modulating it with a frequency, or is modulating the actual frequency of the signal sent. And the reason why most FM radios sound better than AM radios isn't just because they're higher in frequency, but it's because most natural events are amplitude based. So that's why if you're listening to AM radio, you can hear lightning strikes around you, for example. However, there are not many natural events which are frequency modulated. So anyway, I'll turn on some modulation for this guy. Wish I could show you what was on this screen, but I sort of ran out of room for stuff. I just got lost.
Not supposed to admit it.
I'm not supposed to do that. Okay, we got that back. So can you actually see it woggle back and forth a little bit?
Yes.
Yes.
Okay, so that's FM. That's actually a 10 kilohertz deviation. That's about what handheld walkie-talkies look like. Which I suppose I could easily demonstrate with these radios, but my problem with these demos is I'd be happy to show you anything afterwards, but I could run out of time really fast. So on to some more things. So now you've seen AM and FM and FSK. Cool. But Tempest is really kind of like a super rigorous Part 15. You've probably all seen Part 15 compliant on the back of things. Does any of you know what it actually means? Okay. That's what I'm here for. So Part 15 compliance is what the FCC forces device makers to go through so that your laptop doesn't interfere with your cell phone and electronic devices can sort of coexist in electromagnetic harmony without confusing each other. Now, the limits for Part 15 are actually fairly high, and they let a lot of different things through. And you're also supposed to be able to accept any interference if you're part of Part 15. Sounds kind of silly, but that you can't give off any interference, but you must accept any interference that you're given. But anyways, Tempest sort of expands on this by essentially cutting off all of the methods of signal transmission that you would ordinarily have in a device. So what they're going to look at is the grounding of a system, the literal metal Faraday cage shielding around a system, and they're going to look at how much information you could glean from looking at the power supply of the device.
So this is like actually looking at, like hooking into the AC circuit and
Yes.
looking at how the device changes the AC circuit to try
Exactly.
and pull bits. Okay.
And I'll have a demo with that in a second. There's some concern about smart meters Because you can actually get an excellent profile of someone's day by looking at how much power they use. In fact, I recently read an article about being able to tell what television programs people watch by the power consumption that they use. I would have to say that personally I'm not enormously concerned about it, although some individuals on Slashdot are, as I'm sure you believe. But essentially, you'll resign yourself in regards to Tempest safety and just say, no consumer electronics are safe. And this is actually a fairly real concern, especially with the proliferation of consumer electronics devices into the hands of military servicemen and women. Because there's a lot of use of cell phones, iPads, regular laptops, stuff like that. And if they're handling non-sensitive data, it's fairly A-okay. But for sensitive information, they're simply not constructed to these expensive, complicated military standards that would prevent any snooping. Although laptops and computers are quite shielded, and that's because they do put out a lot of radio energy. This computer has a magnesium frame around it. A lot of other laptops, you'll see the plastic is coated in some sort of metallic material to the ground of the laptop. Desktop computers are, of course, a big metal box. And so they do try and cut down on that. But the other big thing about Tempest is you say, well, if I've got to do this really freaky shielding stuff, and I've got to use really expensive power supplies with huge capacitors on it, do I really have to do that on my device? The answer, of course, is no. Because what they're concerned about is this concept of red versus black. Red information, they would say, is, say, for example, sensitive plain text. So say you've got this text file, and you want to transmit it, I know this is going to sound really archaic, over your radio terminal, your data terminal, back to base. And you have your keyboard that you're entering it in with, you have your display, and you have an encryption box and a radio connected to it. So everything before the encryption box will be classified as red, but everything afterwards is black because no matter what anyone looks at it, you hope that your encryption is good enough that it doesn't really matter. Now, the issue there in that system, what would be an example of a vulnerability in the system I just mentioned? Anybody? Any ideas? Maybe.
For each keystroke, you can pick up the
Exactly.
signals.
Keyboards are bad. Not only does each key often sound different, unless you go back into your good old Model M days where it's so loud you can't actually hear any difference between them. But they also put out different electromagnetic spectra depending on what's pressed. And I suppose if I had more time I could have come up with a demo with one of these guys that could probably show you what it looked like when I was typing on my keyboard. The other thing is that you've got radiators and rectifiers everywhere. All of these cables, even though they're shielded, are giving off information. Now, it might not be particularly interesting information, and you might not be able to tell what it is unless you looked at it for several months, but they could give off sensitive information. There are also a lot of rectifiers around, things that turn that electric field or magnetic field into a signal. So say, for example, anyone here ever have any weird issues with their GSM cell phones and speakers?
All the time.
Yeah, da-da-da-da-da-da-da-da-da-da-da. That's because in most amplified speakers, the amplifier contains essentially diode components inside the amplifier circuit that are actually parts of the transistors used that is rectifying that radio energy back into audio. GSM just happens to be at sort of a perfect storm frequency for harmonics, which is why you never want a GSM phone if you do professional audio. But anyways, so there's a type of radio transmission system that's not AM, it's not FM, it's not FSK. It's called SSB, which stands for single sideband. And so an AM signal on the spectrum analyzer, if it looked really perfect, you're putting a lot of information on a fairly high frequency. You see these two sidebands and a carrier frequency. These would be symmetrical, and they'd be giving off the same data. You could take one of these away, and you still know what's going on, but you need a more complicated circuit for it. And these are essentially riding on the power of the carrier. Now the issue here is that you're wasting transmission energy on putting out this carrier that doesn't have anything to do with what you're saying. And so with more complicated vacuum tube radio systems in the late 30s and early 40s, they figured out that you could just get rid of all of that and devote all of your power into one of the sidebands. This lends to an interesting demo because with this system, if this is your transmit power and it's AM modulated, this is actually one-to-one with your voice. Now the even more interesting thing here is that it's actually one-to-one with the current use of the radio. So let me grab a whole bunch of different things here. This is so much fun. So here I have an SSB radio. This right here is a certain kind of magnetic field probe. It's fairly calibrated. It uses something called the Hall effect to look at the magnetic field around a wire. And you can use it to measure the current flowing through a wire. The nice thing about this is that it has a fairly good frequency response, and so you can look at really fast events on current lines. And a device like this would be an example of something that they would use to inspect the current usage of a device compared to what you're doing with it. Now, this will take me just a second. Okay.
It's like all the way over here.
Oh, yeah, I know. Nice. So let's see. Oh, look at that. Here we have on time domain exactly what my voice looks like, and I'll turn up the power on the radio to make it a little bit more discernible. Right now I'm just dumping it into a big resistor in this can. So, wow, that's really beautiful. So you can see that there is indeed information being passed on to my power consumption. And actually, if you're up here, you can look at the current meter on this bob along with my voice. This, of course, is an example where an oscilloscope is better than a spectrum analyzer, because in a spectrum analyzer, all you see is different peaks corresponding to the frequency of my voice. But I wonder if we could actually hear this, and so I can plug more things in. And hope it doesn't blow up.
Wait, so we're hearing the current?
You'll hear the current, yeah.
Okay. I'm just checking.
Yep.
You mentioned we were seeing the frequencies of your voice. Does that mean that you have like a whole bunch of like overtones or something going on?
Basically, what you would see is, I'll show it in a little bit. Basically, what audio spectrum looks like. This little board here is just an amplifier.
operate this. So here you can hear exactly what I'm saying, just from the current consumption of the radio. It will sound a little bit like a demented dog, but you can still figure out what I'm saying. Now, from the amateur perspective, this is a big problem. If you don't know what frequency I'm transmitting on, you're just looking at what power, even if I'm sending something encrypted, you know that I'm sending radio information. Because not many things do this with current. So, yeah, it's a problem.
Now, on AM, you'll hear in a second, it's actually a lot less distinct because a lot of the power is getting converted into that carrier. But it certainly is still perfectly discernible. And actually, what if I turn down the power?
So the first one was the single sideband?
Mhm.
Okay.
If I turn down the power, it's even higher fidelity, which is a little concerning. I mean, it's kind of amazing that it works as well as it does. And I was a little bit startled when I first figured this out.
So wait, are the speakers plugged in directly to the current sensor output?
Yes, that's exactly what's going on.
Why don't you walk us through what's plugged into what?
Sure.
Yeah, what are all these boxes?
Yeah.
Can we turn the lights on?
Yes, I will.
All
Oh,
right.
blue box and a pink can.
Yes.
Sort of done.
Yes, it is.
It's all plugged into the wall.
Building networks are also everywhere, and you can look at those too, but. So, here's a power supply, a fairly large DC supply. So that radio was pulling about 15 amps when I was talking. DC 13.8 volts. Here we have a current probe, and you can see that it's actually like a transformer that's cut open and then slides shut. Going into the radio, and the radio, in turn, is transmitting over this coaxial cable into this thing. It's put together in about 1967, but
And it actually is a pink can. Fantastic.
full of things that typically now you make it with mineral oil. This has transformer oil of questionable provenance. It's also pretty strong. There you can see a resistor that it has in it. It's actually, for the curious, at 50 ohms, which is the impedance of all RF equipment. Basically, it's video.
Oh.
You need to have something to transmit into with the radio, because if you don't have anywhere for your load to go, if anyone is familiar with the concepts of reflected versus transmitted power in the complex vectors of stuff, it will come right back into the radio and cook it. It's not something I'd like to do, because the other thing about radios, well, I mentioned before, none of the stuff is cheap. Single sideband radio transceivers start at about $750. And we'll go up from there gleefully. So that isn't the schematic. That's the block diagram of this radio. The schematic actually covers this back page and another sheet just like this. This goes to show how complicated our things are. But
So
where was I? Yes.
you said the radio was pulling like 15 amps?
Yes.
Why do you need 200 watts to just transmit into a, like,
So-
did that give you anything, or could you have done the same with 500 milliwatts?
So, to make the demonstration work better, the more power I pull, the more distinctive that current signature will be, to a point where it will start distorting. This radio is capable of a power output of around 100 watts. It uses a class AB amplifier. For any familiar with that? Basically, you've got two transistors. They have to be biased, and you're wasting energy to heat because that's how transistors work. Part of the expense in this stuff is the RF transistors I just mentioned are complicated manufacturing, cost about $100 each. It's got 2 of them. So basically, the reason why it was pulling that much current was because it allows me to look at something really easily. Now, radio power, you sort of get diminishing returns the more you transmit. Amateur operators actually have the capability of transmitting up to 1,500 watts, which is a little bit frightening. Especially the higher you go in frequency, the power density will get to the point where it's easy to lose your vision or hurt yourself pretty badly. But I guess while I have all this stuff out, I will do another current example on something that might be a little bit more familiar to some of you. Have you seen one of these before? Okay. I actually figured this trick out while I was at work over the summer, looking at the current of one of these lovely little WRT54GLs, because we do unspeakable things to them at the company that I work for. And one of them was getting turned into a solar-powered VoIP telephone for a strange one-off project. And I needed to figure out how much current it was using. So, let's see.
Why the hell not?
Yeah, exactly.
Can you repeat that? A solar-powered VoIP telephone?
Yes.
Okay. Got it.
This is a much smaller version of that other Holophonic probe. It's not quite as hilariously intimidating.
Does he look like a ray gun?
How much do the current probes cost?
This is probably about $800. This is probably about $400. It's all really expensive. It's really frustrating. Whenever in the open source community is like, I'll make an oscilloscope, except they make it really bad. So it's a problem. Lockman's working on a digital oscilloscope right now. It's pretty cool.
Martin's crazy.
Lockman is crazy. I'm not gonna.
We now have all of this on tape.
I've told him that many times.
I told you, Tyler, if you said anything blackmail worthy in the next 2
So
hours.
we just turned that power and I guess I'll turn this guy on again.
What is that?
Oh, we're listening to it now. I never actually tried listening to it. It's kind of disgusting. So that's rising tones. They're actually listening to the power supply warming up.
Is it so? Are the beats like? Well, I guess they're not beats. Is that the beacon from the radio?
Exactly.
Okay.
So could I theoretically record this audio and then play it back into the router and like...
No. And the reason why is right now we're looking at audio frequency. So even if we feel like we're getting important information, our bandwidth of data being gathered is insufficient to glean information from the system. So
Can we turn off the?
No, we can't.
I think that's how Apex Twin records his music.
So what's the blue box?
blue box, this.
Yeah.
So this is the amplifier for the current probe.
Okay.
It requires a lot of special power supplies, and also has the calibrated scaling, so that when I change this knob to say that there are 5 milliamps per division on my scope, and my scope is at 10 millivolts per division, everything is copacetic. Hold on just a second. So can anyone see without me pulling up the document camera, or is it hard to see?
It won't be on the front.
Pardon?
You can see from here.
You probably put it on the document.
Yeah.
Sturdy.
So these little pulses, which would look a lot better if I had one of the nicer scopes,
It's working.
are all of the beacon pulses that's putting out. And actually, if I were to connect my laptop to it and start pulling data down, you can get a fairly good idea of when data transmissions are occurring. In fact, if we wanted to play around with that some more,
Do you actually pull bits?
back in the days of TEMPEST, you could actually use a telescope to go through someone's window and look at the activity lights on the hub.
Oh, God.
And it was slow enough, and the lights were connected in such a way that if you had a high bandwidth enough optical detector, you could actually completely demodulate the data that was being transferred over the hub.
That's awesome.
Yeah.
So,
Can't really show you that anymore because hubs.
no more for
So much?
gigabit Ethernet? So what you're saying is, yes, you could pull the data out using this thingy?
Yes, if you were the NSA and had a lot of time.
All right.
The trick is, there is a power supply in here that has nonlinear components that are used to change the voltage. And it's important to note that for these two things, I was measuring the DC current consumption. The AC current consumption behind all these different power supplies is going to get increasingly garbled and increasingly difficult to pulling information out of. Which is why I didn't do it, so that the demo worked. So,
But theoretically, with even more time,
yes.
you could pull something out of AC.
Exactly. Let's see, is this the laptop power cord I cut open? No. Oh, yeah, I did. Okay. I thought I was going to have to cut my power cord again.
You realize you avoided your warranty.
Fortunately, I don't really worry about warranties on power cords. Ew. Okay. So, that's the current consumption on my laptop right now. Keep in mind we're looking at the AC line, and so hence sine wave. This is actually, believe it or not, a digital oscilloscope. So we're going to acquire that trace so you can see what it looks like. And we'll actually compare it to what happens in a second.
So is that based, what is that waveform of? Is it based
That's
on
the waveform of the AC input to my laptop's charger.
If you
No.
took out the battery from your laptop, would it change the way the signal looks?
Yes. In fact, it would make it even easier to see what was going on. But I'll pull up a YouTube video and play it in 1080 and see if we get something different on this screen.
I like how Facebook launched things like this thing based on
So I guess I'm a little biased about videos.
You don't say.
So let's see. Got this waveform. I don't actually know if this will work because usually I take the battery out, but we'll see if it's any different. Now we're looking at both waveforms. Do you see how the solid one is smaller than the less solid one? The solid one is our acquired waveform, and the less solid one is what's currently going on. If I stop the video, you can see that it's slimming back down to normal again. If I pulled up Adobe Premiere and started doing really crazy things, it would probably be more evident. But I'm not going to do that. So that was a bunch of different little demonstrations about current monitoring. Current monitoring is interesting because it's hard to protect yourself from it. Often in military devices, they will either use resistors or large capacitors or a variety of other devices to make the device consume more power than it ever could during operation, so it looks like it's just a light bulb consuming the same amount of power all the time. That's one of many different techniques. But essentially, it's like obfuscating your code except with waveforms.
So the power supply on my computer, while it was working, had a giant capacitor in it.
Yes.
Such that when the power blipped for, say, half a second, my computer would still run.
Yes.
Would that help me in any way?
Yes.
Okay.
Part of the issue is that the power company really doesn't like switching power supplies because often they will pull all of their energy out of a single portion of the waveform. And if I have my older laptop's power supply here, you'd actually see that the current was just these weird spikes. And so the current was not matching the voltage, and so it would cause issues with something called power factor, which created standing reflected power. Power company doesn't like it, so a lot of bigger power supplies are starting to incorporate something called active power factor correction. Needs big capacitors and a variety of other things, and so it's starting to mask things a little bit more.
Is it an Android Euro now?
Yes.
Computer power supply?
Yes. Here's another view of one of the Sonobui consoles. So if you've got red and black equipment in the same rack, you've really potentially got issues with things radiating to places where they shouldn't, which is why you can see that everything, of course, is screwing into a metal frame that's probably grounded somehow, except you're always going to have grounding issues if you're in a plane because you're in the air. What I thought was interesting when I was walking through this aircraft was that there was a noticeable hole where something was. I'm really curious as to what it was that they took out. That's like the coffee mug.
That's actually a coffee
Can we tell
maker.
what kind of coffee?
Yeah, actually, if we look at the power signature of their coffee-making appliances, you can really tell if someone had drip coffee, French press, or espresso, though, by the power signature.
So yeah, where did these pictures come from?
This was me pretending to be Russian at the air show a few weeks ago.
Oh.
So here you see a wiring harness in another aircraft, and you've got all kinds of stuff. I mean, these are signals just for operating the aircraft. They're radio communications. These are big coax lines. Radio information, some plumbing. And so when you're designing this system, if you're planning on carrying encrypted information, you really have to think pretty hard about what is in what bundle next to what. Because if you've got all of these E fields and B fields bouncing around, who knows exactly where they'll go. And sometimes, if they had something particularly sensitive, they would just put a metal pipe around it. And some kinds of coax cable are called hardline, and they're essentially what would happen if you took a piece of plumbing pipe and then stuck another wire inside of it. Compared to something with a braided shield, not much is getting out, although you're not exactly bending around any corners of it. This is another example of a variety of different radio equipment sitting next to itself. This is from a helicopter, actually. And here's a row of radios from that same aircraft that were before. And these would be devices that would be experiencing red to black transitions. And you can see right here they have ground braid lugged down to the frame of the device to try and prevent emanations coming out of it. And the way I knew that these were encrypted radios was you can see they have these ports right here in the middle that say fill on them. What they mean by fill is filling the encryption key, which they would do on a occasional basis. So.
Like the Chief Wahoo stickers.
Yeah. So, has anyone ever heard of Van Eck freaking? Yeah. So, CRTs are AM transmitters. And you go, oh my god, and then you realize we don't use CRTs. But, they also had another really interesting capability that Van Eck didn't go into, and I'll talk about how Van Eck exactly works in a second. And that was you could take a telescope and point it into the window somewhere that a CRT was, and actually record the high bandwidth light variations because it's scanning the screen. And decode an image as well. So not only was it vulnerable to electromagnetic waves, it was also vulnerable to light, because it is a scanned and refreshed display system. VGA is an analog cable. You've got 3 coax lines in each carrying red, green, and blue. You've also got some sync signals that are bouncing around all over the place. And if you recover the if you generate your own sync signal, sort of like how a single sideband radio has to generate a carrier with something called a beat frequency oscillator, you can reconstruct the image because of the electrical signature floating out in the air of the different deflection coils in the screen and the way they are all operated. And you think, oh, well, it has problems because it's analog. When we go to DVI, we'll be fine because it's really high bandwidth and it's digital. Nope, it's even worse. So I wish I had come up with a demo for this because I realized that it would only take about a week to build something to do it, but this is scary. But because of the way DVI operates, and you've got these different, they call them TMDS data lines that are going up and down and up and down and up and down. It actually is, in effect, modulating a radio signal for you. And they can be picked up at relatively long distances, and I have a couple of academic papers on VANAC and on DVI attacks that I will have add a link for you guys at the end. But all digital logic, as I mentioned earlier, is a transmitter. And that's partly, in effect, because you have these high to low transitions that create harmonics and other energy that's bouncing around. And also because everything has a clock. And actually, if I took this radio, say tune it to the frequency of the graphics card on my desktop and wave it around, you can hear it. Tune it to your processor clock, you can hear it. All of these clock signals are bouncing around. And that's actually one of the main reasons why computers are so shielded, is because if they weren't shielded, they would not only interfere with everything around themselves, but things that you have could also disrupt other stuff on your computer, of course. And Steelcase isn't interrupting those cosmic rays, but no one cares about ECC RAM, do they? But why won't ambient light attacks work on LCDs? You may know.
They don't do a scan.
Yeah, they don't scan. They only update when the data changes. So you can't look at the temperature of light in the room and figure out what's going on. So there's all sort of different kinds of things. You can actually do replay attacks by looking and recording the radio signal of a device and then playing it back to itself. You can use different computer programs to analyze the protocols that you're looking at. Often fairly simple protocols that date back to the 70s are used on non-critical things, and you can start pulling all these different telemetry data streams out of the air if you're really that interested in, like, say, for example, what temperature the parking garage is. But I mentioned earlier an interesting vulnerability with GSM. It was discovered at DEF CON that the major GSM telecommunications providers had turned off the warning message on all of their cell phones regarding connecting to unencrypted towers, because they were under the impression that if they had any unencrypted towers floating around, they would want to scare their customers. Well, the way GSM works, your phone is going to connect to the strongest tower near you, so if I happen to have, for some reason, a cell phone tower in my back pocket, which would be pretty impressive, your phone would preferably connect to my tower instead of the other tower. And if I poked around into the telephone network and made the calls reroute with VoIP the way that you would expect your call to go, you'd be none the wiser, and suddenly you have an enormous man-in-the-middle attack on your phone calls. It's a little bit more complicated than most Tempest, but just an interesting example. I'll give some protocol examples in a second. Does anyone recognize this? I know you recognize this. This is an example of a HID compliant 125 kilohertz RFID reader, identical to the ones used at CASE, unencrypted, no handshake. They're pretty fun. So, out of general curiosity, before I move on to what I was actually going to demonstrate, I will look at the current line of that reader. Because, for example, if your power supply isn't adequately filtered, you could see when power was being consumed on the line to send the door and lock codes. Because these RFID readers use a protocol called WeGAMD, where they have two 5-volt data lines, and they pull down the 1 line for ones and the 0 line for zeros. It's really very strange. But so was the 70s. 70s. Oh, look at that.
Yeah,
I will do it.
What affects the effective range of the RFID scanners?
Several things, including how many things you have behind them in your pocket, but the major determinant is the transmit power in the reader itself. So if you were to construct a reader of your own contrivance, especially with a directional antenna, that instead of transmitting at several milliwatts, transmitted at several watts, you could point it at somebody in a room to read their card.
It'd
Didn't
be
hear
very
it from me.
convenient if you didn't have to be literally on top of the readers in
Yes.
indoor buildings
Well,
for them to read.
the
those.
ones for the parking lot.
Those ones are big.
Yeah,
Those
you
are-
can actually read. I
Through
think
the
our
car
record was
window.
6 feet.
Yeah.
Yeah.
away.
Yeah, and that's why if you ever see
Oh,
like
that's
Richard
cool.
Stallman at a conference, they give him an RFID card, he wraps it in some
That does less than you would think. In fact, the best way of shielding one of these RFID cards is to simply get another and put it behind it. Because if you have two devices beaconing at the same time, they can't figure out which is saying what. And
So I need a HID compatible RFID card. My Metro card won't work.
no, that's why you can still swipe with your wallet.
Yeah.
So who wants to give me their case ID? Anybody?
Wait, it's actually not flag, it's
Here.
it's just
Just to show.
the rapid card.
So I'm either sure there's another this works, but as you can see, both of the cards are back to each other.
So you can take some.
It has absolutely no idea what's going on.
But does it matter if they're the same type of card? Because I
They both have to be 125 kilohertz cards.
They actually
Whether they have to be the same protocol or not, I don't entirely know. These cards, of course, are powered by the reader, and that's why a higher powered reader would be able to read them from a longer distance.
So if I want to protect my passport, I should just get another one.
Jason Bourne.
So the tinfoil doesn't actually really work.
It could, however, the problem is you might just be making another antenna around itself. Because if you're not grounding your Faraday cage itself can act as another antenna.
Okay. Has anybody told Richard about this?
So
Would you do it one more time?
There we go.
I think the actual problem here, or not problem, the only information that's being transmitted about the power is just the beeper. Because the current being used to beep overwhelms any of the current being used to decode the card. Of course, I've got a spectrum analyzer. So, by the way, if you want to hear this thing beacon, it sounds really obnoxious. But, there are a lot of RF connectors. There's 5 different kinds in this table.
Has somebody done a musical skit with this stuff?
I'm sure someone has.
Oh, I really want to record that.
Yes, it does, actually.
Like, it just sounds totally badass.
Because you can hear the data burst.
No, I'm thinking more like
That sounds like
I want to point that signal at
sandstorm right there.
I want to point that signal at Seti and see what happens.
What does the timer make when you use like 2 cards?
You probably wouldn't hear anything. If you looked at the spectrum analyzer, though, you can actually set it so that it shows what normal is. And even though it sounds kind of strange, antennas actually suck the energy out of the air around them a little bit, even though it sounds kind of like troll science. And you can actually tell that there would be something trying to pick it up that wasn't really succeeding at it.
Can you turn off the lights so we can
Yes.
What is this world of patience?
So, let's see. I have a lot of really short cords.
That man's very confused.
It's the best part. Yes.
Oh.
Now somebody's been saying
Why does it look like it's doing the wave?
That's because it's a waveform. Hold on a second.
everything and everything.
So this is actually really, really ugly. The big spike on the left again is DC.
So it's digital.
So
Where
you
are
can
we
see
supposed to be
this,
looking?
this rising pulse. Let me see if I can change. So you can see that stuff shifting around the bottom edge. That would be the beacon. The issue with these analog spectrum analyzers is you can see how it's sweeping across, and I can change the sweep speed, but that's going to impact my resolution. So also really confusing to use compared to oscilloscopes. Let's see. Let's see what. So there you just saw a fairly large bump of data. You've got to get synchronized right for it to do anything. But I wonder. This is that normal mode. So if it knows what's normal, then it knows what's not. When I bring my card closer, you see it's slightly changing. And that's because the active components in the card are impacting the transmitter, because it's got inductors in it, things, physics stuff. Anyway, so RFID, fun stuff. Anyway, any questions about that? Bored yet? Great.
So if you wanted to like inject a signal into that to say open the door, would you be able to through this?
Trivially.
Excellent.
Yeah.
Alright.
So wait, it's kind of tangential, but how do the card readers themselves update?
So the card readers on campus actually operate through a central database.
Okay.
Um,
So they all like network.
yes, if you look at your card, yeah, when you swipe your card, basically it pulls the server. Server says yes, no. That comes back to another computer hidden in a closet. Not really a computer, mostly a computer. And then it says either open or no open. And it sends a signal to the reader that toggles the LED or beeps at you or whatever. If you look at the back of your card, you'll see two groups of numbers. The first group of numbers is actually the code sent when it gets scanned, as well as the number 233, which is Case's facility code. But anyway, before I get in a lot of trouble,
By telling people listening on the video how to open any door on campus.
I can take that part out.
Well, no, you need a valid ID to open the door.
well, I
that's
won't
why I
go
asked
into
how-
any more about it, but I can assure you that you can find out things on that internet thing that I think some of you are interested in.
Sorry, this is slightly unrelated, but as far as opening doors is concerned, with the swipe keys on the doors in, I guess, all the south side stuff and the village, they are not attached to any power source. How the heck are they powered?
Oh, I know how
Recharge
these
the
batteries.
batteries.
I know how this works. So I figured out that they
You
don't
ask Marcel.
update until you swipe the new card.
Yeah.
Yeah.
So your old card is active until the new
Yeah,
card.
the
is
new
swiped.
card is,
It has a rewrite code on it.
yeah, the new
Really?
card exists in a
Yeah.
special
If anybody would like to
state.
spend $30, I have a very interesting attack. I'd like.
Yeah.
There's other cool
Talk
things
to
you
us
can
after
do,
class.
like for example, read your door card and then put it on the useless little US bank stripe on the back of your case ID. But anyway, So what's new in this? I mean, mostly what I've been talking about hasn't changed a lot since the 70s. And, but a lot of things are advancing further. Not only are there new things to attack, and not only are computers getting faster and spraying more bits out into the ether, but improvements in analog to digital converter technology have spawned something new called software-defined radio, which basically functions like the oscilloscopes in the other room. You're taking an analog to digital converter, and you're actually sampling at the radio frequency you want to look at. And if you're not sampling at the radio frequency you want to look at, you're using a heterodyne receiver to shift it down to make it easier to look at. Because in order to decode it, you run back into Nyquist theorem. So if you were to want to decode a 500 megahertz signal, you'd have to be pulling down a gigasample.
Is this what Bob's working?
Pardon?
Is this what Bob's working?
Yes. Other computer processing improvements have led to digital signal processing. That radio right there can reduce the noise and actually filter the audio using a DSP chip, which will work better than any analog filter that you could contrive for it. An even better system, used in more expensive radios, is actually using DSP on the IF block, right where the bandpass filter is, which will prevent your demodulator circuitry from getting overloaded by certain other extraneous signals. So it allows you to look at things even more closely that are weaker, as well as a variety of other cool things. It also is allowing things like computer sound cards to encode and decode radio protocols instead of having to resort to using using dedicated hardware. So that's pretty much it. I've got a few extra demos if anybody wants to stick around with those sound card protocols and stuff. But if you have any more questions by this, I'm not going to claim that I'm an expert, but I'm certainly interested. And if you want to look at some other papers, there's a link. It's a directory listing. There's 3 PDFs.
Do you host that computer?
Yes.
So you're the guy that hosts the mirror picture?
Yes.
Yes.
Okay.
Wait, what can
We'll show you.
Off camera.
Yeah.
So anyways, Spectrum.
Oh, wow.
So this is a free program called Spectrum Lab. It's fairly hard to use, but it's made by some crazy Germans. But it is an excellent FFT spectrum analyzer. So if I pull it up,
I love those tabs. They're just labeled 1, 2, 3, 4.
so does this look reminiscent of the spectrum analyzer?
Yeah.
So here we've got our frequency across the top, or it's supposed to be across the top. Where'd it go? Anyway. Hold on.
Sweet, what's the input for
The input for it currently is my laptop microphone. There's a delay on it right now, and I don't quite know why. If you want it to work really well, you use a sound card that uses ASIO drivers, or low latency, if you actually are interested in what I'm talking about. I don't know if you actually are. But, let's see. How do I make this thing work faster with this? Let's oversample the sound card faster than it could ever run. Maybe it'll work. You can see that we're losing resolution, but it is responding a little faster. So a lot of these spectral systems change over time, and if they're changing over a fairly long period of time, it's hard to see what they're doing if you're just looking at a graph like this. And that's where something called a spectrogram comes in. And basically what you do is you take the frequency component and you use it to sort of color this falling, they call it a waterfall display. Sometimes they scroll left, sometimes they scroll right, sometimes they scroll down. And keep in mind this is a much narrower band that that spectrum analyzer is dealing with. This is only 5,000 hertz. But in the audio range, this is what we're used to dealing with on everyday life. So if I whistle, you can see very clearly what was going on right there. And you can actually see harmonics of it above. They were picked up by the microphone.
Huh.
So where does this come in with other things? So say, for example, if we wanted to look at what the RFID reader was doing, we connect this radio, and I have the cable for this in the other room. I just didn't get it because microphones work remarkably well. So you can actually see it's got this periodic thing about it. And you can get some information from it. Really, spectrum analyzers that are probably running an operating system of their own actually have these built into them. There you can see the pulse. Keep in mind that the frequency of that sound is of no relation to the actual signal. That's only what my radio is interpreting it as. So when you heard it drop, that was me changing where the radio was tipped. Because it was actually reading in single sideband mode, and so it was creating a carrier for itself, as I mentioned. If I pulled it up on AM, you just hear pop, 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 as the carrier was keying on and off. So let's see, what else can you do with spectrums? So this is a program typically used for amateur radio communications. Also free, much easier to use. And you'll see that it also has a, let's see if it's on this microphone. Yep, okay. Also has a spectrum display. And there's a bunch of different protocols that operate on a bunch of different principles that are all connected by the same fact that you can use them just by using your computer sound card and your computer processor to encode and decode them without any special circuitry. So if you want to hear what every science fiction movie has in it all the time, or sort of what everyone thinks of as
That's nice.
well, that isn't what was supposed to happen. Strangely enough. Hold on just a second. What it just tried to do was key up the radio with a serial signal, whereas all I want to do is use sound. So let's see. Well, that also didn't work.
I'm beginning to worry that the people who design these tools don't understand user interface design.
They don't.
They don't.
It looks muted.
And now you feel like we're fighting the Russians again.
So could we use this program to decode the 56K modem beats?
No, but you could use a 56K modem to code the 56K. You could use this, however, to listen to weather fax transmissions that or weather information transmissions that are still being carried on by the National Weather Service as information sent out to boaters in the Atlantic Ocean. They also send a colored fax, actually.
They sell colored fax?
Yes. Over radio to boats.
Of course.
If you want to see what colored fax sounds like, that's a weird picture. Although it's actually one of the BBC's older test cards. That's what that actually is. That's not what I want. That's what I want.
That mirror picture.
Yeah.
That's also not what I want.
Creepy.
Was there?
There we go.
So now I have to remember how to transmit with this program, because I haven't used it in a while. The funny thing is that I tried to download a program that I like a lot, except they used really bad web code and kept claiming that I was trying to leech their download link. Bad.
Because
Anyway.
you have to upload it before you can download it.
Come on, Tyler, what's your wish?
Why can't I key up? Where's the button? Has to be a button.
There it is.
So you can hear it sending the you can see the spectrum of the signal on the top right. It has these synchronization pulses, and it's actually sweeping across the image and giving the information out. Any of you have this software on your computers, you'd probably pick it up and you might want to decode this with fairly high resolution. There's a bunch of different protocols for it. The slower you go, the better it works, except the slower it is. Some of them take minutes. Do you really want to listen back in 5 minutes? I mean, maybe you do. I do. 28, Merritt's eyes.
That's what they sound like.
So radio teletext, what I just showed you, worked by the way, this is not part of my presentation, I'm just talking. I don't know why you're saying this. But radio teletext works on having mark and space pulses. So you have this data that's getting sent 170 hertz away from itself, and you can actually change the shift if you really want to send something that no one would be able to pick up. And these mark and space pulses are being alternated based on a code corresponding to letters that isn't ASCII, because ASCII didn't exist yet when they invented it, because originally mechanical machines would do this. It's actually something called Baudot code. Some of you may be familiar. It's 5 bits. It actually has a signals versus figures line, which is how it fits all the numbers and letters into 5 bits. But anyway, you can even change the baud rate for all these things. Speed it up. But RIDI is fairly old, think 30s. A newer one invented actually by a radio amateur is called PSK, and it uses phase shift keying and works similarly well to Morse code. The funny thing about Morse code is that even though it's the most efficient transmission protocol that could exist, because you're going between full output power and no output power, computers are really bad at reading it, which sounds strange, except it's difficult for them to stay aligned with the signal that may be shifting around, which is very common in these lower frequency radio communications, because they are heavily dependent upon solar weather and the level of ionization of the ionosphere. I can give another talk on that, but I don't really. Anyway, here's a really cool one that the Germans also came up with during World War II. It's actually another fax system, and it would work by having different wheels printing the text out on a strip of paper. And if you have issues with the frequency shifting up and down, the letters will shift up and down, but because you have signals above and below, you'll probably be able to figure out what letter was supposed to go where. So it's actually remarkably robust.
So instead of giving you the letters, it's giving you the actual dots in the text.
Yes. There's all sorts of other things. Some protocols have a lot more error correction than others. You can see this is a lot more wideband. For amateur stuff, there's often a fairly high people like really narrow signals because you can fit 4 of them in a small space. But the wider your signal is, you might have advantages when it comes to error correction. So anyway, yep.
So I know from experience that police, a lot of times, will have unencrypted data terminal
Yes.
transmitting over the air.
Uh-huh.
And would something like this be able to like encrypt it?
Well, often, so I don't actually have a program on my computer right now, on this computer that can do it, but There are packet radio standards that are fairly common. One is 1200 baud, really, really slow, but still very common. There's a lot of things out there, and if you spend enough time trying to figure out what it is, you'll probably be able to figure out what you're looking for. I'm curious to look at what these D-field probes look like because I've never used one before. So, anyway, I'm not compelling any of you to be here. Right? All of you understand, right?
Well,
Josh, you want to wrap up the
Yeah.
presentation before you?